Hello, physics class. Hope you guys are doing well. I'm going to give a little presentation here on magnets and magnetic fields. We have a 1 week long crash course on magnetism. I'm going to break that up into 3 bite-sized chunks, and the first chunk is magnets and magnetic fields, and we're going to go quickly. So this whole slideshow is available on Canvas as well. For starters, I hope you're all doing well. I have great concern for your welfare, and I hope that you have not just what you need, but what you need to thrive and not just survive. If you feel like you would like to talk about physics or this class or Canvas or school or virtual learning or anything beyond that, and I could be of help, I'm happy to do so. You can just reach out by email and we can work out a conference call or something. And to cast our mind back to those carefree pre-COVID days, I have a short video of me juggling that makes me happy. And it's so short you didn't get to see it. Here it is. Oh, that's all. I think why I like that so much is because you can barely see my hands. It almost looks like the things are just flying up on their own will. Okay, here's what we're going to try to do today. I hope that by the end of this week, you'll be able to, in given situations, predict whether magnets will repel or attract each other, and describe the magnetic field around a permanent magnet, and describe the orientation of Earth's magnetic field. And we're off. Magnets, a brief introduction. We have kind of the philosophical question of what are magnets and why they work the way they work. And if you're like me, I went through a period of time when I really struggled philosophically with what in the world, how magnetism worked, that just drove me batty. Here's something to remember, and take the advice of this young physics prodigy here playing with magnets. We don't have to really understand how they work, or like the philosophical fundamental how they work. In the same way that we don't really understand why gravity works, but we just accept it because for 17 plus years you've just been happily living with the fact that gravity does work. We're going to have to happily live with the fact that magnets work as well. Electromagnetism and gravity are 2 of the 4 fundamental forces in the universe, and somehow with gravity we don't ask these difficult questions like, yes, but how does gravity work? We know the formula, and we just accept that it works. We'll learn the formulas for magnets too, and we'll have to accept that they work, and they work in a similar way to gravity with all its mystery. So we're going to have to embrace the mystery of that. We're going to pretend that every magnet we discuss here in this class for the week is a bar magnet, straight line bar magnet with a north end and a south end. So a north and south, and if you cut this bar magnet in half, you don't end out with a south end here and a north end here. You end out with 2 bar magnets with a north end on the top and a south end on the bottom. And if you cut those 2 in half, guess what happens there? You're right. You get 4 bar magnets with north ends on one side and south ends on the other. No matter how finely you cut them, you still end out with a bar magnet with opposite ends on opposite sides, opposite magnetic poles on opposite sides. And so for the uses of magnets, it's really difficult to grasp how useful and how used they are in modern life. Anything that uses an electric current has to take into account magnetism or generates magnetism. Sometimes that magnetism is just a byproduct of the use, and sometimes it's useful in its own right. But the computer you're on, the phone you're on, the lights in the building that you're in, the electric toothbrush you use in the morning, that all has some magnetism associated with it. So one of the cooler uses, I think, is magnetic levitation trains that are getting used in Europe and Asia. These trains can go super fast, have very little friction attached to them because the train isn't actually riding on rails. It's levitating above them using magnetic levitation, so maglev trains. That's, I think, is the coolest thing right now. MRIs, magnetic resonance imaging is also useful in healthcare field, that kind of thing. Okay, so what you need to know about a magnetic or bar magnet is north repels north, and south repels south, but opposites are attracted to each other. So north and south attract on a bar magnet. And we'll come back to that too. That'll be important. Something else you should know is about number 2, magnetic domains. A magnetic domain is a region composed of a group of atoms whose magnetic fields are aligned in the same direction. So we're going to look at 2 little images here. Here's some kind of piece of, doesn't matter what, piece of iron, we'll say. And magnetic domains are these little areas that are just represented by little bar magnets. And these can be, I mean, it's not like individual atoms. It's a small piece of the iron. And that small piece may be a millimeter in size, down to 1,000th of a millimeter in size. And inside this little domain, the magnetic orientation tends to be the same. It all acts like a little bar magnet. But for the whole piece of iron, all the orientations kind of counter each other. They offset each other because the random orientation makes this not function as a magnet. If you could take these different orientations and line them up, then you would have made a magnetized iron bar, which you have down here at the bottom. So the movement of electrons is what creates a magnetic field. So if you have electrons zipping around in the atoms here, which you do, those moving electric charges create a magnetic field. That's the way that magnetic fields are generated, is by moving electric charges. Unmagnetized domains have a random orientation. They cancel each other out, so it's not magnetized on the macro scale. Domains can become aligned and become magnetic domains, like down here. So this is a bar magnet. Some materials can be made into permanent magnets. So magnets can be easy to form or hard to form. If they are hard to form, they tend to hold their magnetism well long after they're formed. So, but if they're easily magnetized, they're also easily demagnetized. But some can become permanent magnets. Something to know. Now, magnetic fields. A magnetic field is a region in which a magnetic force can be detected. When we talk about force, we don't mean the same thing that Obi-Wan Kenobi meant when he told Luke to use the force. We mean force in the physics sense equals mass times acceleration. That formula is not that helpful, honestly. Here's a better formula. Remember the formula for work? Of course I do, Mr. Yevon. That's good. It's work equals force times distance. So if we divided both sides of that formula by distance, you'd get work divided by distance equals force. That's really what we're talking about. A magnetic field is something where force can be detected, work can be done across a distance. So we mean it in that sense, something capable of doing work. And a magnetic field is a vector quantity. It has both a direction and a magnitude, and that whole thing, the direction and magnitude, are represented by the capital letter B. You want to know about why it's B? Me too. I don't know why. Magnetic field lines can be drawn with the aid of a compass. I'll show you what that means here. So this is a bar magnet, north end and south end, and you have iron filings that have been scattered about it, and those iron filings orient themselves along the lines of the magnetic field. So in addition to that, a compass, if it's placed in any one spot, the arrows of the compass will align themselves with the magnetic field. So if this is the north end, this arrow here is pointing that way, the north arrow is pointing that way, and here the north arrow is pointing that way. You can see the north arrow moves through this arc back down to there, so on those 7 compasses. So the direction of the magnetic field is indicated by the direction that a compass would point at a specific location. Iron filings and compasses will align with magnetic field lines. The direction of the magnetic field is defined as the direction that the north pole of a compass points. So at this spot, the direction of the magnetic field here is that away. Magnetic fields are vectors. Here we're talking about the direction of a vector, but a vector also has a quantity. So we need a term to describe that quantity, and that term is magnetic flux. Magnetic flux relates to the strength of a magnetic field. Magnetic flux is defined as the number of field lines that cross a certain area. I'm going to show you a formula. I hope you're all seated. The good news is we're not going to use that formula this week, which means we're probably not going to use this formula again, which means this may be the only time you see it. But here it is. Brace yourself. There's the formula. Phi sub m equals AB times cosine theta. Here's what that means. Phi sub m is magnetic flux. It's the strength of the magnetic field. And we calculate it by taking the surface area, or A, times the magnetic field component normal to the plane of surface. That means B, the magnetic field, and then cosine theta means the part of the magnetic field that's perpendicular or normal to the plane of surface. Okay. So there is the formula. You should know that there is one. If we had this class in person, we'd probably take this formula out for a test drive once or twice, but we don't have time or the ability to do that right now here the way we are. But we should know it exists. Now, Earth has a magnetic field similar to that of a bar magnet, and you have seen this image before with an Earth and a giant bar magnet inside it, and magnetic field lines emanating and circulating around and leaving one pole and entering another. Here's our philosophical question that we're going to close with. If the Earth is like a bar magnet, which magnetic pole is at the north end? Look at the direction the arrows are pointing, and look what's up here. The south magnetic pole. So here's what I mean by that. If this compass is pointing north, and this one, and this one, and this one, and this one are all pointing north, we know that the north end of a bar magnet is attracted to the opposite end of another bar magnet. So if Earth is one giant bar magnet, the south end of that bar magnet must be up here at the North Pole, because my compass, the north end of my compass, points toward the south end of Earth's bar magnet. Did that make sense, or is that the sound of your mind being blown? That's really all we have to go on. This slideshow will be posted on Canvas, and in the meantime, you should go be awesome.